Hello everyone. Today's class about operational amplifier and applications. Let's start. When you see the outline of this chapter, you will see introduction of op-amps, ideal op-amp versus practical op-amp, parameters of op-amps, op-amp applications, basic op-amp circuits, inverting amplifiers, non-inverting amplifiers, summing amplifiers, that means other, differential amplifiers, that you can call it subtractor, integrating amplifiers, we can call it integrator, differentiating amplifier, we can call it differentiator. So we will see all about the op-amp from the introduction up to the application of op-amps. Now let's start. What is an op-amp? The operational amplifier or op-amp is a circuit of components integrated into one chip. So that means in single chip, that is the integration of different components like transistors, resistors and capacitors. So an op-amp is a high gain amplifier which is used to perform variety of operations such as amplification, addition, subtraction, integration, differentiation, etc. So an op-amp used for addition purpose, for subtraction purpose, there are the application of op-amp. And also to provide voltage amplitude change, value change. So amplify the value, and also change of polarity. That means in phase or out of phase. Often used to amplify small signals. An op-amp is expensive, efficient, versatile, and readily available building blocks for many applications. That is popular type of electronic component. So operational amplifier is a high gain differential amplifier with nearly ideal external characteristics. Internally, the op-amp is constructed using many transistors. So advantage of op-amp over conventional amplifier, that's what you learned in the previous class or in other course in fundamental principal electronics about how transistor amplify. But this op-amp is the integration of electronic components. So advantage of op-amp over conventional amplifier: it has small size, it has less power consumptions, it is easy to replace, low cost and high reliability. So the terminology of op-amp or terminals or parts of op-amp: V plus, we can call it non-inverting input voltage. That is the plus symbol, we can non-inverting input voltage. V minus, we can call it inverting input voltage. That means when our input is in this side inverting, so our output is invert. But when our input is in non-inverting, our output is non-inverting, but amplify our signals. V out, that we can call it output voltage. I out, we can call it output current. Non-inverting current, input current, that's here, plus symbol. Inverting input current, that here, plus minus VDC, that is, we can apply positive VDC and minus VDC up from plus minus 5 volt to plus or minus 30 volts we can apply. So sometimes the supply voltage connection not shown in the circuit when referred in different textbooks. Change of voltage: V non-inverting minus of V inverting, it becomes difference voltage. That's how to, when both inputs are signals, the difference voltage becomes from non-inverting minus of V inverting. You can call it difference voltage. Packaging of operational amplifier. So it looks like this IC type, the popular type of type of op-amp is 741 type of op-amps. Operational amplifiers are available in IC package of either single, dual, or quad op-amps within one single device. The most commonly available and used of all operational amplifiers in basic electronic kits and projects in industry standard microampere that you can 741 type of op-amps. So the pin configuration of SN741 type of op-amp dot beside, that is from start pin this one, we can counterclockwise number 1 pin 1. So input is pin number 2 V inverting, pin number 3 V non-inverting. So inverting input voltage, non-inverting input voltage. Output pin number 6. Pin number 6 is RV out. Power supply, we applied negative VDD pin number 4, positive VCC pin number 7. Pin number 1, number 5 for offset control, for offset controlling system. So in single op-amp, these are the pin configurations of op-amp. Op-amp we can go in metal packages, op-amp single IC, op-amp in dual type, that means in single IC 2 op-amps, quad 4 op-amps in single ICs. So the op-amp simple, it looks like this one. It has positive, negative, that's non-inverting, inverting, high power supply, low power supply, positive, negative, and output. So internal model of real op-amps, it looks like this feature. It has input impedances, difference voltage V1 minus V2, that is non-inverting minus of the inverting, open loop gain between them, that is output impedance again. So let's see ideal versus practical op-amp. Property of op-amp. During ideal op-amp, infinite voltage gain, infinite bandwidth, infinite input impedance, zero output impedance. So perfect input without any loss and perfect output without any loss. But practically it's differ. High voltage gain range from 10 raised 4 up to 10 raised 7. High bandwidth, some ranges. High input impedance 10 raised 6 to 10 raised 12 ohm. Very low output impedance from 50 up to 75 ohm. So we will summarize in this table ideal versus practical op-amp with their property: voltage gain, input resistance, input current, output resistance, bandwidth, common mode rejection ratio, slow rate, V out, power supply rejection ratio. So we will see one by one. So the internal block diagram of an op-amp. A typical op-amp is made of 3 types of amplifier circuits: a differential amplifier, a voltage amplifier, and a push-pull amplifier, as shown in this figure. So as we said, op-amp is made up of integrated circuits with different transistors. So the first differential amplifier provides amplification of the difference voltage between 2 inputs, between non-inverting and inverting. Voltage amplifier usually class A amplifier that provide additional gain. So op-amp may have more than one voltage amplifier gains in the voltage amplifier gain. So push-pull class A amplifier typically used for the output voltage. So at what time the op-amp saturates? So the op-amp is when you give a small signal in the output to amplify. So how to control that, or at what ranges saturate that op-amp? Note that in spite of the huge gain, the maximum or minimum output is still limited by the input power. So limited by the input power, that by the applied voltage. When the op-amp is at the maximum or minimum extreme, it is said to be saturated. Ideally, the saturation point for an op-amp are equal to the power voltage. In reality, they are 1 to volt less. So that means a negative V applied voltage less than or equal to V out less than or equal to positive V applied voltage. So that means V out during positive, approximately positive volt applied. That is positive saturation. V out approximately same with negative voltage during negative input voltage. That is negative saturation. So our V out, then this is our V in this graph. The graph that relates the output voltage to that input voltage is called the voltage transfer curve and is fundamental in designing and understanding amplifier circuits. So in the negative side, negative saturation; in the positive side, positive saturation. Note that the two distinct regions of operation, one around Vi becomes 0 volt, the linear region where the output changes linearly with respect to input, and the other at which change in Vi has little effect on V out, the saturation region, nonlinear behaviors. So circuit with operational amplifier can be designed to operate in both of these regions. In the linear region, the slope of the line relating V out to V in is very large. Indeed, it is equal to the open loop gain. So for example, for a 741 type of op-amp, power with VCC plus 10 volt and VCC minus 10 volt, V out will saturate or reach the maximum out voltage ranges at about plus or minus 10 volts. So not exceeded from that our applied voltage to the op-amp. So how they operate this op-amp? In simple way to understand, when our op-amp in negative V inverting more greater than V non-inverting, our V out becomes negative saturation. When V inverting greater than V non-inverting, our V out is negative side. But when V non-inverting larger than V inverting, our out becomes positive. So by this principle, the op-amp we can work. So that means V difference becomes V inverting minus of V non-inverting minus of V inverting. By this principle, our V out. If V inverting is larger than V non-inverting, our out becomes a negative. If V non-inverting is greater than V inverting, our out becomes positive. By this principle, the op-amp is worked. How an op-amp configure? Op-amps can be configured in many different ways using resistors and other components, active component or passive component. Most configurations use feedback. Feedback is a technique where a proportion of the output of a system or amplifier is fed back and recombined with input. So from this output of op-amp back to the input, we can call it feedback. So different types of feedbacks. Mostly two types of feedback, that is positive feedback and negative feedbacks. It has own advantages and their applications. As you see this picture, the first feature we can call it negative feedback. From the output op-amp, so this resistor back to the input of negative sign. So we can call it a negative feedback. In the second feature, as you see, from the output of op-amp, so this resistor back to the positive side of the op-amp. We can call it positive feedback. So a negative feedback, as information is fed back, the output becomes more stable. Output tends to stay in the desired range. Example, cruise control, heating or cooling systems. Most amplifier type of op-amp is used a negative feedbacks. In positive feedback, as information is feedback, the output destabilizes. The op-amp will saturate. So this type of positive feedback used in oscillation system or oscillators. So let's see the advantage of negative feedback. A negative feedback is the process whereby a portion of the output voltage of an amplifier is returned to the input with a phase angle that opposes or subtract from the input signals from the output back to the negative signal of the op-amp. This we can call it negative feedback. This lowers the amplifier gain but improves freedom from distortion and nonlinearity, flatness of frequency response or conformity to some desired frequency response, stability and predictability, and also insensitivity to variation in open loop gain. So that means in negative feedback our amplifier becomes predictable. So this means that is controllable by this feedback. So that means this op-amp from open loop gain to gain of closed off gain. So amplifier with negative feedback depend less and less on the open loop gain and finally depend on the property of the feedback network. So from the open loop to the closed loop gain is by the means of a negative feedback. So let's see some op-amp parameters. It has 6 or 7 parameters of op-amp. The first one, input bias current. The input bias current is the DC current required by the input of an amplifier to properly operate in the input current. That input current, the average of both V1 and V2. The input bias current is the average of the currents into the two input terminals with the output at 0 volt, which is typically around 80 nanoampere. That means 80 times 10 raised negative 9 ampere for a 741 ampere. That is popular type of op-amp. The input bias current causes a volt drop across the equivalent source impedance seen by the op-amp inputs. The second one, input offset current. Ideally, the two input bias current are equal and their difference is 0. But in practically op-amp, however, the bias current are not equal. The input offset current of an op-amp is the difference between the two inputs current with the output at 0 volt in 748 on op-amp becomes 20 nanoampere. So without applied voltage or input voltage or current, we get voltage difference between V1 and V2 is 20 nanoampere during input offset current. Input offset voltage, the third one parameter, for an ideal op-amp produces 0 output voltage for 0 input voltage. However, practical op-amp produces some small amount of DC voltage, few millivolt or in microvolt, as output even when input voltage is 0. Therefore, input offset voltage is the differential DC voltage required between the input to force the output to 0 voltage. So again, without any applied input voltage, we can get some microvolts or millivolts in the input. That is difference of voltage V1 between V2. The fourth one, output offset voltage. The voltage which is produced as the output when both inputs voltage V1 equal to V2 becomes 0, that means non-inverting input voltage equal to V inverting voltage becomes 0. R0 is 0 offset voltage, the voltage present at output without any input applied. So that we can output. That's what I see in the pin configuration of the op-amp. Pin number 1 and pin number 5 is for offset adjustment. So without any applied of the voltage or input voltage, we can get some in millivolt or in microvolts in the output or in the input, in the voltage difference. The fifth parameter, common mode rejection ratio. The ability of an op-amp to suppress common mode signals is expressed in terms of its common mode rejection ratio. So as the same input polarity, it has some unwanted signals are inserted in the op-amp. So it's rejected by common mode rejection ratio. The sixth one, slow rate. The slow rate of an op-amp is the maximum rate of change of output voltage in response to state of input voltage. So what does mean? Slow rate is the rate of output voltage changed caused by step input voltage. It is measured as a voltage change in a given time, typically volt per microsecond or volt per millisecond. Mostly for 741 type of op-amps, the slow rate becomes 0.5 volt per microseconds. So let's see, in ideal, slow rate is infinite, which means that the operational amplifier output should change instantly in response to an input step voltage. So this is actual, this is what the outputs, but this is ideally what we see, but actually like so. From this input change to this output, how many volts per second or how many volts changed? Effect of op-amp in slow rate. Ideally is perfect as is input, but actual output is changed from this to this one, is some difference. So how to measure or the equation of slow rate? It is relatively easy to calculate the slow rate of an amplifier that is required for a given application from a knowledge of the maximum voltage and frequency required. To give distortion-free operation, the slow rate of the amplifier, the simple formula below can be used. The slow rate becomes 2 pi multiplied by frequency, again multiplied by V maxima. So the slow rate is measured in volt per second. Also actual measurements are often given in microsecond or in millisecond, voltage per microsecond or per millisecond. F the highest signal frequency, V is the maximum peak voltage of the signal. Let's simple example. Take the scenario where an op-amp is required to amplify a signal with a peak amplitude of 5 volts when our voltage is 5 volts at the frequency of 25 kilohertz. An op-amp with slow rate at least 2 pi 25,000 multiplied by 5 volt, it becomes 0.78 volt per micro will be required. So in each microsecond it's required 0.785 change of voltage from input to the output. So slow rate measure in op-amp connect as shown this feature. From this input as out, this is our input, what was in the output. So step in voltage and resulting out voltage. So another equation, we can calculate slow rate, change of V out over change of time. So whereas change of V out or voltage difference, V maximum in the positive minus of V minimum in the negative side, that is change of volt, or voltage difference between two, V non-inverting minus of V inverting. You can calculate it, or you can get a slow rate. Let's see example. The output voltage of a certain op-amp appears as shown in this feature in response to step input determines the slow rate. So the change of the voltage from this negative line to the maximum stable output up to this positive line, so change of V out becomes positive 9 minus of negative over 1 microsecond. The difference between this minimum voltage to the maximum voltage is 1 microsecond. So over 1 microsecond, so becomes 18 volt per microsecond. That change from the input to the outputs. So this is a slow rate. That one parameters of op-amp. It has different another parameter thermistors and supply voltage rejection ratios. so we can refer textbook as that written in the textbook.